Okay, I'm Dave Dugan. I'm the president of EBTRON. Today I'm going to give you a presentation on on airflow measurement for healthcare facilities with the idea of primarily improving healthcare air quality, but also saving some energy by doing things properly. Okay, so when it comes to healthcare facilities, I'm going to be pretty blunt on a few things I say today. I hope it doesn't offend anybody. But basically, when it comes to improving healthcare facilities, we really need to make sure that we have accurately measured the supply airflow rates. The reason we need to do that is we need to control and verify room air changes per hour. Okay, that's going to be very important. There may be other reasons why you want to do it, but that is a very important reason. And then there may be some of you that use equivalent clean air to reduce outdoor airflow rates. So if you're doing that, I think it's even more important to be able to show that you've actually provided the supply airflow rates that you need as the equivalent clean air flow rate. Getting into like outdoor air, we need to accurately measure outdoor airflow rates so that we can control and verify outdoor air changes per hour. Outdoor air is an extremely expensive thing, but it's very important too. So, you know, we want to provide what we need. We don't want to provide too much. We don't want to provide too little. And then finally, the thing that I want to talk about is room pressure control, particularly in operating rooms and spaces like that. It's really important that we do flow control. There are challenges with flow control that we're going to talk about, but that's how we want to really control room pressure. And then really we want to think about whether or not, from an energy perspective, we can actually do an unoccupied setback operation. And in my 40 years, I have not seen that work, and I have a pretty good handle on why I think it doesn't work. And so I want to talk about some things that I think we can do to make it so potentially we can go to unoccupied setback mode where it's allowed. So, you know, that's basically what we're going to talk about, but the way that I want to talk about it is going to be in segments. And so we're going to talk about air changes. I mean, we don't have an infinite amount of time here. Okay, three hours sounds like a lot, but it isn't. And so we're going to talk about air changes. We're going to talk about outdoor airflow control challenges and what we need to do about that. We're going to look at different outdoor air determination methods. You know, maybe you're not a believer that we need to directly measure it. So I want to look at some of the other things that we do. Pressurization. Pressurization obviously is very important in healthcare facilities. And we're going to do some control strategies. Now, I try to generalize those because typically the audiences I have, do more than just this healthcare. So if we generalize the airflow control strategies, you can take them to the next level. Okay. And then, finally, we're going to talk about technology. All right. So that's the basic. That's the basic plan. Well, when it comes to air changes, okay, what are we talking about? Well, we're going to be talking about room air changes. I call them room air changes and outdoor air changes, okay? Sometimes people call them different things, but, how much air are we changing in the space? So if we don't have any outdoor air or any filtration, targeted high-level filtration, what is going to happen? Well, what's going to happen is we're going to have the contaminants build up in the space. And even though we're talking healthcare, this could be just about anything, okay, right? It doesn't have to be a healthcare facility if there's, it could be any facility that you have. Okay, so what can we do about it? Well, I like the way that healthcare talks about it because it makes more sense to me. Standard 170, we're not going to go into details of Standard 170. If you're listening to me today and you do healthcare facilities, I think you pretty much understand Standard 170 and what your requirements are. So I'm not going to bother talking about that. But the big things in Standard 170 is air changes and the role of air changes. And so basically, when we talk about room air changes, it's all about filtration. How many times does the air pass a filter, okay? And that's why we have room air changes. And then outdoor air changes is all about dilution. How many times do we dilute out the space? And so when you take a look at it, you have filtration, okay? And we can remove a lot of contaminants with filtration, but typically speaking, filtration alone isn't going to do it all. So we also talk about outdoor air changes for dilution. And so again, outdoor air isn't going to do it all either. So it's a combination of the two. All right. So the fundamental requirements for contaminant control in healthcare facilities is going to be a combination of room air changes for filtration and outdoor air changes for dilution. That doesn't mean you can't do anything else in addition to that. I'm not saying that, but I'm saying these are the fundamentals. And, I do a lot of work in non-healthcare facilities, and I find that a lot of folks are ignoring the fundamentals, trying everything else they can do for air quality, but forgetting the fundamentals. Fundamentally, this is what we have to do. Okay, we have to remove the contaminants through filtration and dilute the contaminants with outdoor air. Okay, that's just going to be the way it is. All right, so that's this little short segment on air changes. It's pretty short. It's pretty simple. Okay, so we're going to talk. To me, understanding measuring supply airflow for room air changes is pretty straightforward. I mean, you want to use good instrumentation that's going to last a long time, that's going to be accurate, and you don't want to have to really deal with it. Okay, but when it comes to outdoor airflow rates, it's a little more complex. Okay, outdoor airflow rates are going to be something that you just can't set and forget, and there's reasons for that. All right, and the reasons for that can be, we could have fan speed changes. Okay, we could have systems that are VAV in nature, or even even if we have some dedicated outdoor air systems, there's kind of some similarities there too. But the thing that gets overlooked a lot is wind and stack pressure. What's going on the outside of the building, and how do those pressures affect the amount of outdoor air that's actually coming into your unit. Okay, I think it's fairly significant, and I want to show you that. All right, and then if we're talking about air handling units, we also have to deal with dampers, and the fact that there are a lot of issues with dampers. And so it's not a set it and forget it type of thing. In fact, I'm going to demonstrate to you that when I say this, outdoor airflow rates can vary by more than 50% of the desired set point. If you just set it and forget it, I'm actually being really nice. It could be considerably more than that. So the question is, why is that? Okay. All right. Well, this kind of dates me, but it doesn't matter. I've been, in a way, I think this is kind of sad too, that I've been able to use this paper that we published in 1990 in ASHRAE journal, and I still use it as part of my presentation today. And the reason I think that's sad is because not everybody's made the connections here. Okay, now this paper I thought was a big deal. It was written primarily, the primary author there, David Solberg, was really the guy behind this, and he saw things and probably still does before everybody else. Okay, and so back in the 70s and 80s, we had indoor air quality problems that resulted from the energy crisis of the 70s, and ventilation rates were reduced. And ASHRAE decided to do something about it and significantly change Standard 62 in 1989 to bring the ventilation rates up. And so seeing that what was going to happen there, we wanted to get ourselves in a position where people realized that they couldn't do what they were doing, which was just set it and forget it, and they needed to measure and control outdoor airflow rates. So I'm going to just kind of give you a simple look at this, okay? If you've been to any of my presentations, you've seen this, okay? Because I always do this. But it never hurts to see it a few times. So I like to do this with just a simple recirculating air handling unit. It's the easiest one to understand. And because I only have a supply fan here, it's the easiest one to actually demonstrate, okay? So here we have a system, and let's say it's a system with a, supply fan only, no relief at the air handler, which, isn't going to be the case in a lot of our healthcare applications, but it really won't make any difference, okay? It's just, this is easy way to look at this, okay? So the intake system, if it was just a fixed damper, is a fixed orifice, okay? So it's got a fixed flow coefficient. And so that as we change the supply air fan speed, we're going to change the supply air flow, and the mixed air plenum pressure is going to change with it. In this case, if I reduce the supply air flow, I've reduced the mixed air plenum pressure. Over a fixed orifice, the outside air is going to drop, okay? And if you looked at the pressure relationship, I'm going to take an example where the total pressure drop across that intake system at design is 0.3 of an inch. That might not be your system. Your system might have a 1/2 inch. Your system might have more than a 1/2 inch. My system might have less than a 1/2 inch. We're going to pick something because we want to be able to have a discussion about it. Although I will say in this format, it's not a discussion. It's just me telling you what I'm going to tell you. But if you looked at the mixing box plenum pressure in this system, it would follow this basic square root relationship, okay? As the supply air flow drop, the mixing box plenum pressure would drop. And, I'm going to just go from 100% supply to 60% supply there on that horizontal axis. And in this particular example, we'd almost have a 0.2 of an inch change in pressure. And that 0.2 of an inch change in pressure would have resulted in a linear reduction of the airflow rate. That's what happens on these systems, especially this simple recirculating air handler. So we go from 100% to 60% supply. The outdoor airflow went from whatever you set it to 60%, okay? Now, I think that that's pretty well understood by most people. I don't think they always look at that it's not just VAV, that it's constant volume with multiple, variable speed, or at least even just 2-speed fans. It's also fan coils. In a little different way, it's DOAS to multi-zone systems that have some kind of demand control ventilation. So, I'm looking at it as a VAV system, but don't think it's only VAV that has this problem, and don't think it's only a system with a supply fan, supply return fans, supply relief fans. They have the same types of problems. It's just harder to demonstrate a general, make a general discussion about it. I also have some slides that I haven't put in here for damper reset. That doesn't work as either, okay? It may help compensate for some of these problems, but it's not going to compensate for this next problem we're going to talk about, which is what happens when the pressure change isn't in the mixing box, but it's on the outside of the unit. I mean, it really doesn't matter. If it's a fixed orifice, it's a fixed orifice. If you change the pressure drop across it, you're going to change the flow. All right. So we want to look at what exterior surface problems we could have, and what are those particular sources. Well, it's wind for one thing, and even though this is like what I'm showing you here, the illustration is of a rooftop unit. It doesn't matter if it's ducted or not ducted. You have pressure changes from wind. You may protect those intakes a bit on the roof, but to be honest with you, they're going to be affected by wind pressure changes, and stack pressure changes. You're not going to protect that at all. If I have the illustration on the right side of the screen is, hey, I have an air handler on the roof serving the first floor. Well, the first floor, that's a big hole in the building that's connecting it's only serving the first floor, so the return duct's a big hole in the building that's connecting the first floor to the downstream side of the intake damper. So when you go from winter to summer, you have stack pressure problems, not like you think of for affecting floor pressure, but just for affecting what's going on at the air handler. And we're going to show you it's not just high rises, okay? So when you go back to this slide that we had and looked at this 0.2 of an inch change causing a 40% reduction, you know, you could get the same 0.2 of an inch change on the other side of the damper, okay, simply by having the wind change. And that's why I like to talk to a lot of test and balance people, because it's like, hey, you're going out and you're setting some of these systems up that don't have control or are relying on damper position, you know, and you're having these problems because what you don't realize is that the pressures are changing. So what you set today isn't what's going to happen tomorrow. So here I have an 18 mile an hour direct wind to an 18 mile an hour crosswind is about that same 0.2 of an inch change on that intake system. And so that's a 40% change in the flow. Okay, and when you plot it, you know, you look at on the supply airflow, you go all the way to the right here and you look at 100%, you know, full span speed, you know, that's where the 40% is going on, okay? But now as you reduce the supply airflow, you kind of compound it, you have now the changes in the mixing box plenum pressure, plus the changes in the outdoor pressures. And so you end up with outdoor air that's between those two red curves. And look at your set point is what I showed there as that dashed black line at 100%. So, you know, in some cases you're going to be over ventilating, but in a lot of cases you're going to be under ventilating, okay? And you can even turn your intake into an exhaust, really, okay? And so that's wind pressure. And then, you know, this is from actually our building. We monitor and look at wind speed and things like that. And really, we just, one day, you know, we set the building up on a calm day, no significant wind, and we set it up for that black dash line at 100%. And we came back on another day where we measured a nominal 15 mile an hour wind down the side of the building. So it was a negative pressure on that intake, and if you looked at the average flow, it was almost a 20% reduction. And the reason we put the scatter on it, the scatter is the actual data that we took, and the reason we do that is we try to explain to people, it's like wind going down the side of a building isn't a constant speed, and it's not a constant direction, so it's moving quite a bit, you know, magnitude and direction. And we try to explain to people that are trying to control this that a lot of the errors or problems we see with folks doing outside air control is the output of their control loops are too aggressive, too fast. Slow it down because you can't compensate for these wind pressure changes with an actuator. Okay, you want to kind of want to look at the average flow, and then you want to control though actually to the actual data. And people say to me, "Well, I'm not seeing that on the supply side." It's like, no. The further you get away from the source of the wind, you know, the further you get away from the unit, the air is compressible, so it kind of gets dampened out. Okay, you'll see changes, but you won't see them as rapidly. And that's a whole nother discussion, and we don't have time to do it today, but there is a right way and a wrong way to take the signal from a flow measuring device and control outdoor air. You know, we're not in an environment where the wind doesn't blow, okay, and we need to not forget that. Stack pressure, very similar. I have a 70-foot low rise, 100-degree swing in temperature, you know, same 0.2 of an inch. Now, some of you are in cooler climates where you'll see more. Some of you are in more temperate climates where you see less, but the bottom line is it's a problem. And if you just set it and forget it, there's no way to compensate for it, okay? And you get very similar type of deal. Winter stack problems are worse than summer stack problems, but, you know, because the offset in temperature is typically more. And when you combine the two, which is really what happens, you know, the wind blows and the temperature changes, really any system that's depending on damper position cannot effectively maintain outdoor airflow rates. It doesn't matter what it is. Okay, so that's what we have to do here. Okay, When we take a look at air handling units again, or anything that depends on dampers, I mean, dampers are oversized valves, and even the best ones aren't the greatest control valve, okay? And so the problems you have are three. We have hysteresis. Hysteresis I'm actually going to demonstrate on the next slide. Hysteresis is just, hey, bring the drive shaft back to the same exact position. Are the blades in the same position? And the answer is no. Okay? Never mind the fact that really actuators have built-in hysteresis so you don't burn them up. Binding's pretty straightforward. Linkage binds, you know. If you are going by straight damper position, and it can bind enough to break linkage. So I've seen systems in my career where if the actuator feedback looks good, you know, hey, my damper is supposed to be at this position, and it is. And then you go look at the damper, and the linkage is broken, and a couple blades are hanging in the wind. You have no way to know what the flow rate is, okay? You feel good. You have a false sense of security that your feedback signal is telling you you're okay. And the same thing is true with deterioration. Deterioration of seals, for sure, are a huge problem in dampers. It changes the opening, okay? So these are all problems, and this is just, again, some data that we have, and we did it. This is a pretty good damper. I mean, I am a big fan of Tamco dampers, and this is a Tamco damper. And then we take it from basically, you know, if you look at the two data sets there, the red and the blue, okay, the red is we took it from night setback or closed to 15% open and measure the outside air, okay, and that's the red, and I think I got that right. No, the blue, I'm sorry. And then the red, we took it from 100% economizer, okay, back to that same 15% open, the same signal to the actuator. And when we measure it, we have two very different populations that are 20% apart in flow. And that's just hysteresis. That's nothing else. So again, you can't rely on damper position. I mean, it's not just in outside air intakes either. It's everywhere. You can't do it. It doesn't work. Okay, so we have to compensate for that. Okay, and when you look at the whole deal, you look at all these different factors that influence intake flow rates, and really, you really should come away from this saying, yeah, I need to figure out how much outside air I have coming into this system, and I'm going to need to control it. Okay, and that's really where I want you to be right now. Okay, I don't necessarily want you to be where it's like, oh yeah, I have to put a flow meter directly in the outside air path, but I do want you to be in the, hey, I better do something about this because I can't rely on damper position or multiple damper positions. I have to figure out how much outdoor airflow, what's the outdoor airflow rate coming in to the system, whatever system it is. Okay, so that's where I want you to be now. Okay, let's take a look at how we might figure out or estimate how much outdoor airflow, what the outdoor airflow rate is coming into a unit, okay? You know, without maybe directly measuring it. Okay, so what could we do? Well, one thing that's been around for as long as I have is called the temperature ratio method. I called it adiabatic mixing when I was younger, and some people call it the energy balance method. It doesn't really matter. What it is it's based on, you measure the outside air temperature, you measure the return air temperature, and you measure the mixed air temperature. Okay, at least operationally, that's how you would do this. Okay, so you got those three temperatures, and based on those temperatures, you can use a very simple mixing equation and estimate the percentage of outside air in the mixed air, which is the supply air. Okay, so then if you measure the supply air flow rate, you know, theoretically, you have the outdoor airflow rate. Now, people have done this, and people are still doing it, and but there's problems with this, okay? And one of the problems is it's not just, I've heard people say, oh, as long as the temperatures are far enough apart, as long as the outside air temperature is far enough apart from the return air temperature, you can do it. But they're not looking at something real simple here, which is just measurement error in general. Now, I'm going to make this better than actual, okay? I'm going to look at the outside air temperature there on the bottom right. I'm going to say it's 40 degrees. I'm going to do a very specific example first, and then I'm going to do a general one. It's 40 degrees, and it's so good, there's no error in the measurement, which obviously that's not really true, but let's just say it is. And then on the top there, top right, return air, 75 degrees, again, no error. But when we look at the mixed air is not easy to measure accurately. In fact, I can show you with velocity, weighted temperature that it's even by doing that, you could be a few degrees off in some cases because you have a huge velocity profile and a huge temperature profile that you're trying to measure. Okay, particularly with return air and outdoor air. So I'm going to say that the mixed air measurement was 2 degrees uncertainty. Okay, which I don't think is a lot. I think it's actually more than that. So what I'm doing is I'm calculating everything with those measured temperatures, and then I'm looking at the supply flow rate, and I like to pick nice easy numbers, so 100,000. It doesn't matter what you use actually on the supply flows, can look the same way. 100,000 CFM of supply air, again, no error, which is not reasonable. It's probably 3 to 10% depending on what you're measuring it with. But let's just say there was no error. If you went back and did these calculations without a bias on the mixed air, meaning you somehow were able to get the actual mixed air temperature and you did the calculation again, instead of getting the 10,000 CFM that you would have gotten here, which is 10%, those calculations result in 10%, you would have gotten 4,286 CFM. You'd only be 60% off. I don't think that's acceptable. Okay, and I hope you don't think that's acceptable. And so, you say, well, Dave, you probably picked some crazy example. And I was like, no, let me just carry this through to a more broad example. I said, look, I'm going to keep the 2 degree uncertainty, of the mixed air is going to be the same throughout this. No other errors, just like I did on the previous slide. And I'm going to look at different percentages of outside air into supply air, okay, or mixed air. And I'm going to run from 5 to 25%. And when I take a look at this, the errors are huge. They see the little green, it's really small. That's plus or minus like 5% tolerance on the outside air. And obviously, that's not where you're at. And so the method is really terrible. And I tell test and balance folks they shouldn't use it because Standard 111 has this actually in there. And Standard 111 for test and balance professionals says you can be within 10% doing this. And it's not true. You can't. I mean, you'd have to be very lucky to be that accurate. And so I don't like to go with luck. The couple of things you got to get out of this is, one, if you were using this as a control strategy, meaning you weren't using test and balance to do it, there's going to be a lot of error. If you were using test and balance to verify something like our piece of equipment, you'd have a lot of error. There's no way it's going to match. So you just have to be, you have to understand that. Okay, so that method is, to me, it's out. The one that gets used a lot, and it really bothers me, and it's used a lot because a lot of folks will say, well, my air handler comes with piezo rings, and I have supply measurement, I have return measurement. I mean, I'm not showing return fan here, but I see a lot of this, okay, where we're going to take the difference between the two, and that's how we're going to determine what our outdoor airflow rate is, okay? I mean, you're not going to do that if you have relief at the air handler, but if you don't have relief at the air handler, you can do that or use it at least to set things up, and at least in theory. And so here I'm going to say, hey, again, I'm going to measure the supply and the return, and I'm showing air balance doing it, but it could have been permanently mounted devices, and I'm saying, hey, you measured 100,000 on the supply and 90,000 on the return, so you said you got 10,000 CFM of outside air. It's like, okay, but what's the uncertainty of those measurements? And like I said, it's going to run 3 to 10%. Typically, it can even be a little bit more on turn down on piezo rings, but let's just say that they got tweaked in the field to get, within 5 or 10% of turn down. I think it's possible. Okay, I'm going to say no. Let's do something better. Let's use 3% uncertainty. I mean, why would maybe EBTRON should be selling this idea? It's like you'd sell 2 flow meters. Why not? It's like, well, here's why not, okay? At least in today's technology, the way we sit today, it's like, look, if we were plus or minus 3%, that means we could be plus or minus 3%. So when we measured 100,000 CFM, it could be 3% less. So that's 97,000. And, you know, when we look at the return side and we measure 90,000, you know, it could have been 3% more, which is 92,700. So that the difference of 10,000 was really 4,300. And it's not like, I'm not doing rocket science math here, okay? It's just, you got to look at it and say, oh, well, what are the uncertainties of the measurement? And, you know, that's not acceptable. It's not going to work. And so I put in different measurement uncertainties and show, you know, how bad the error is. And really, you have to get under 0.5% to have any chance of 0.5% of reading airflow measurement in the HVAC world. That's going to be pretty hard to do. We're going to talk about some things later that may improve out of the box performance of flow meters, but it's still a pretty tough thing to do. And when you look at those uncertainties there on the left, it's so bad I have to plot it on a logarithmic scale. Okay, that's pretty bad. So make sure you understand that the different curves there are different uncertainties of the supply and the return flow measurement, because you're measuring a differential. So the accuracy of the differential is much larger than the inaccuracy of the differential is much larger than the inaccuracy of the device you're measuring it with, okay? And again, this method is often used as a verification method. Okay, so now you might say, okay, well, yeah, I guess I shouldn't use those two methods. I'm going to do something else. Okay, so what is the something else? Well, we talked about damper position already, so that should be out. You know, I mean, you can't compensate for fan speed changes, wind speed, stack pressure. It doesn't matter if it's one or two position and you have all these damper problems. So that should be out. Mixed air plenum pressure control, though, is something that people do try to do, okay? And what is that? It's like, okay, I'm going to maintain the mixed air plenum pressure constant, okay? And some people do it to the mechanical room, which is a really bad idea. Other people put it across the damper, which is a better idea, okay? Because then you're getting some component of wind and stack pressure, okay? But the problem is it relies on damper position. And there's no way to know if the damper has problems. The things we talked about regarding damper, hysteresis binding and deterioration. And it's also pretty hard to control. Okay, so there's no real positive verification of flow. The only thing you have a positive verification of is that you've maintained this pressure drop or pressure point. Okay, so I'm not a real fan of that. Fixed orifice airflow measurement. So that's, you're using the louver or something else as a fixed orifice. And, you know, one of our competitors does that. And, you know, on an intake system, those are very, very low pressures. And there's also, you know, I look at that, I say, okay, well, it's like saying to you, I'll put a one sensor flow meter in an outside air intake, or two sensors. There are velocity profiles, massive velocity profiles on intakes. I've seen 10-to-1 velocity profiles on intakes, and they move, they vary, they're not always the same, okay? And so, you know, you're doing this fixed orifice thing, and if you have velocity profiles, you have pressure profiles. So you got to be really careful with that strategy, as you do if you put in a very low sensor density U and EBTRON, like one or two sensors on a big intake. I don't think it's a great idea for control. So you have velocity profile problems. Regardless, on all of these methods, okay, it cannot be any better than the field measurement, because they all have to be field calibrated. You don't know the flow coefficient of the louver. and particularly when it's installed, but you wouldn't know it anyhow. Mixed air cleaning pressure control, you need to determine what the flow is. And like I said, we'll just forget the damper position ones because they're terrible. And now I say 25% here. I'm really talking rooftop units. Now I will say that when you do more ducted intakes, and a lot of healthcare facilities pay a lot more attention to intake design than non-healthcare facilities, you definitely can get a better balancer measurement, okay? But, you still have these problems. So it's something that you should be aware of. And because I find that not everybody thinks about these things. It's like, oh yeah, that seems like a good idea. It's like, well, it may sound like a good idea, but it probably isn't a good idea, okay? And so the right thing to do is directly measure with factory calibrated devices. And that's really where we're at. And we put in the EBTRON, and we verify it. We do want to use test and balance to verify it. We want test and balance to go look at it, take a look at what their uncertainty and measurement is, understand our equipment and say, yes, it's installed properly, and I've done my measurement to the best of my ability, and it's within my tolerance. If my tolerance is 20% on this particular intake, then I verified it, okay? And one thing that I said I wanted to talk about earlier, I'm going to bring it up a couple times, okay? These flow meters are designed to work and be stable for years and years and years. We have them at EBTRON that are 20 years old, over 20 years old, operating just like they did day one, and we demonstrated at the Brinagast. And some of them are pretty dirty, but they're not so dirty that we can't tell what they are, okay? And I tell people all the time, if you have critical air paths, okay, and you're concerned about dirt and dust accumulating on your dampers and your flow meters and everything else, then why are you bringing that outdoor air in? Okay, you really need to think about maybe doing something to make that air in a better condition. We do lots of outside air flow meters a year, but the reality is some of them do get pretty fouled up, but not most of them. But if you have that bad of a condition coming in, don't shoot the messenger, fix the condition, okay? But anyhow, that's what I want to say about that. But the bottom line is, a 5 or 10% outdoor airflow meter blows away any other method, okay? So that's my position there. Okay, pressurization in healthcare it's important in all buildings, in all facilities, okay? I mean, when we talk about non-healthcare facilities, obviously we think more about positive pressure because we're thinking about keeping what's outside of the building from getting inside of the building, whether it be dirt or dust, pollen, whatever, but smoke, something that we really do need to talk about someday, but not in this presentation. And in humid climates, which is pretty much everything east of the Rockies, then we also have to deal with moisture. Okay, we still have to deal with that in healthcare, but that's not really what I want to talk about here. I want to talk about contaminant exclusion, in spaces because we want to keep things out or keep things in. So, positive pressure space, we want to keep things out. And negative pressure spaces, we want to keep things in. Okay, so what are we really doing? I mean, what are we doing to do that, And it's really, even though we talk about pressure, we've called it pressurization for so long, that's just what we call it. But it's really not so much pressure as flow, okay? So if we have a pressure zone and we have outside air coming in and exhaust air going out, maybe we do or don't have powered exhaust out or relief. But the bottom line is, if I have more mechanical ins than outs, then I've created a positive pressurization flow. And that positive pressurization flow would result in a measurable pressure drop at points in the space, but it's really the pressurization flow that we want to control. Okay, the same thing if we wanted a negative space, then we'd want the outs to exceed the ins, mechanical outs to exceed the ins. And it's pretty straightforward in terms of concept, it's not really all that complicated. But in practice, it's much more complicated, okay? And so one of the things that we want to make sure that we don't do, and I think most people I run into don't do this in healthcare. However, I have worked on enough healthcare facilities that have tried to do straight out pressure control that have downright failed, okay? And because of this one serious flaw, forget talking about the pressure sensor and does it drift, and forget talking about the pressure sensor and is it affected by wind pressure, because really you want to isolate mechanical pressurization, okay? So wind pressure and stack pressure, don't isolate that, all right? So we want to isolate that, but forgetting that for a second, one of the biggest problems when doing pressure control in healthcare facilities in particular is you might have multiple air handling units serving those two boxes or two pressure zones, so that pressure zone, is responding to what that air handler is doing, air handler one. But what air handling one is doing is affecting the pressure of the adjacent zone, which then affects the control of air handler two, which then affects the pressure of the zone one, and it goes on and on and on. And so what ends up happening is that you cannot compartmentalize pressure zones when you do pressure control, okay? And if it's a static condition where nothing's changing in all of these pressure zones, you probably can set it up and make it work. But if you have things that are changing within pressure zones, like exhaust rates changing in different pressure zones, then you're not really going to be able to isolate your pressurization and you're not going to get effective control, right? So that's one of the serious problems with it, okay? They just affect each other. Now, if I was doing airflow control, differential flow control on air handler one and differential airflow control of air handler two, yes, how I change the differentials between air handler one and air handler two will change the pressure relationship between those two zones, but it won't change the way air handler one or air handler two are controlling, so you can compartmentalize. It is a huge and fundamental difference. Another thing is, and this is just a can go, doesn't mean it has to, okay? I mean, a lot of this is a tuning thing, but one of the problems when you do room pressure control is, and this is keeping it kind of simple, okay, so that what we're looking at is the room pressure is the red, and the pressurization flow is the blue. When you do pressure control and you open a door, it can go out of control, okay? And if you had a positive pressure space like this one, it could instantaneously turn into a negative pressure space. Now, you may or may not see that, depending on how fast you're sampling these pressure sensors. So, or if you're integrating it, you might say, well, I don't see that, but it could be happening, and that is something that you really do not ever want to have happen. When you do airflow control, sure, you open the door and again, the pressure drops to nothing. You're not going to pressurize that space, okay? But it stays, the pressurization flow stays where you want it to be, meaning it's still positive, okay? And it's really something that I think most of this audience understands that, but if you don't, you should think about that, okay? Now, this is where I think some people do think about it and others do not, okay? And, these are not on a presentation like this, when you're looking at these slides, you're going to have to go back and look at these on paper to see them, okay? I mean, there's a lot going on a slide here, all right? So here I have an OR, And I have a floor area. If you go to the middle, I have a floor area, I have a design supply airflow rate. I have a pressure set point, and I have an offset, and then I have an accuracy of the flow measurement. And this is actually a pretty leaky space, so it's a pretty leaky space. But anyhow, show you what happens if your measurement was 10%, which so many people say to me, as long as it's 10%, as long as test and balance gets it in with 10%. It's like, no, that's not true. Okay. I mean, in this case here on the left, it shows you, the solid lines are what you theoretically think you have in flow when you finally sit down and look at this. Okay. And then the dashed lines is the uncertainty, plus or minus uncertainty. And if you look at that bottom left graph, you can be really positive or really negative. And what I've done is I've just made an assumption, which may or may not be right, that the relationship, the pressurization flow relationship to pressure is a square root relationship. It's not necessarily that because things change, but let's just go with that for a second. So I calculate a flow coefficient for that room. And so, when you look at that right-hand graph, which is what the actual room pressure is, okay, you'll find that red solid line is what your target was, and the dashed reds are where you could be, and it's all over the place. And what ends up happening, I think, is that you go in and you balance these spaces until you get the pressure where you want them, okay? But if you were going to try to do some kind of a setback, it's not going to work because the measurement is just too unreliable. So setback won't work in this case. You may get it so that you can have all of the rooms working properly at the design condition, but they're not going to work properly at a setback condition, okay? And that's what I want to, talk about and see how can we make this better. Okay, so 10% on this example doesn't work, 5% isn't really much better. 3% is still marginal, and in this case, you'd have to get to 2%. And this is a pretty leaky space. If this space was even tighter, the tighter the space, the harder it is to control it. Okay, so as spaces get tighter and tighter, the control gets harder and harder. Okay, so that's something I want you to think about. Accuracy really does matter. In fact, I can show you cases where even our flow meter, properly installed, okay, out of the box, even if it was 2% accurate, isn't accurate enough, okay? So we're going to talk about that a little bit more at the end when we talk about technology and things we can do there, all right? But accuracy does matter. The other thing that I think matters that our industry is kind of in the dark ages about is everything we seem to do in HVAC is based on actual flow, actual CFM, based on velocity, linear velocity. That really doesn't make a lot of sense, okay, because we have changes in air temperature where we're doing the measurement. We should be thinking more like the process folks and thinking in standard CFM, which is really a mass flow equivalent. And so what I've done here, I'm looking at this. I used this slide for a lot of different presentations. I could have tweaked it a little bit for this. This is really more of my outside air type of one. And when I talk to people about why standard 62 isn't right, talking about calculating outside airflow rates and then, coming up with a rate, and then you set it on one building when it's 10 degrees out, and you set it on another building when it's 100 degrees out. They're not the same flows, okay? But anyhow, here, if you look at the left, that's actual, or what we typically deal with when we go out and measure. Even the way the EBTRON comes out of the factory is actual, because that's what you guys want, or gals, you all want, okay? And so, but I don't know if you realize this, 1,000 CFM, actual CFM at 30 degrees of air coming in, and 1,000 CFM, actual CFM of air at 70 degrees going out, does not result in a net neutral building. It results in a positive building. And it's an 82 CFM positive building. It's 8%. That's a lot. And when you look at, standard CFM, which is the mass flow equivalent, 1,000 at 30 and 1,000 at 70, you get net zero. The reason that this matters is that on the healthcare side is you can get away with this after you set your systems up. If the supply air condition temperatures aren't changing and the return air temperatures aren't changing. But if you have anything that's changing there, okay, you're adding a little more uncertainty to your pressurization. And you really should be thinking about standard CFM, which on the EBTRON is very simple. You just set it to output standard CFM. It's just something I like to put in for those of you that are really doing real precise control, particularly as spaces get tighter and tighter and tighter, okay? So think about that. Okay, so then it's like the don't shoot the messenger, all right? Look, we're never going to get really good flow control and setback control until we realize that we have to filter at the source, okay? I've been doing this for 40 years. Yes, I've seen a lot of flow meters get fouled up. I've seen a lot of EBTRONs get fouled up. I've seen a lot of pitot tubes foul up. I've seen just about everything foul up, okay? We test everything and everybody all the time. We use different materials. We use dry lint. We use wet lint. We use, like this case, drywall joint compounding. It's about as bad as you're going to get, okay? We do different things to see what we can do to overcome some of the problems of dirt, dust, and lint. And the bottom line is when you start talking about needing to have measurements that are better than 2% of reading, and needing to have measurements that are better than 2% of reading for 10 or 15 years, you really need to start to understand that you need to provide a really good environment. If we want to do good control of ORs or ISO rooms or any of those types of spaces, and be able to independently control those as independent compartmentalized pressure zones, it doesn't matter who you're using or who you listen to, okay? We're going to need to provide a better environment. You can take one of our pieces of equipment, put it in the supply air, and I'm pretty confident that 20 years later, it'll be measuring what it was measuring the day you put it in, okay? It's a pretty good environment, okay? But I can be pretty confident that in most healthcare situations, it's not going to be 20 years later. Something's going to have to happen to it along the line. And I don't like that. And it might be as simple as, oh yeah, I clean it. I brush it off or I blow it off. Well, a device like ours, you brush it off, you blow it off, it's back where it was. A pitot array or something like that, they plug up, okay? But most of the time, yeah, you just blow it off, brush it off, it's fine. Great. I know customers that do that. They pull the thing out every couple months and they blow it off. I know other customers that say, I'm not going to use this stuff anymore. And it's like, okay, then you're not going to get the precise control that you need. The answer is very simple. Source filter, okay? Filter at the grill in an OR. I mean, when you open up your grill in an operating room and the duct looks like a chia pet, it should tell you that there's something wrong. And I know it's not necessarily those of you that are the engineers that I'm talking to, but the hospitals have to understand that. Now they start talking about, we can't afford to do this and we can't afford to do that. But when you do this right, and now all of a sudden you can get setback operation that really works, you get good control for years and years and years without having to do any maintenance. I think that's pretty much a small price to pay. The energy payback is great. Okay, you're not designing systems at higher pressure drops. You use other types of technologies. It's the way to go. And I've decided at 62, going on 63 years old, I'm tired of not saying this. This is going to be my position from here on out. Okay? Because that's what we need to do. all right? And I'm going to keep pushing it, and what I've seen, and I'm not necessarily suggesting that you only do this, the cheap blue filter and the return grill, because, there are advantages of pre-filtering a little more of that material out and saving some of your HEPAs and things like that, even though you do have other pre-filters. Not having to do duct cleaning and things like that is a great deal. I mean, I'm going on a little tangent here. I mean, I've seen compounding pharmacies with ducts this big that after a period of time, the inside of the duct is this big. That's a problem, okay? You don't want that, all right? So, and the general term lint is not necessarily what it is. It's lint, it's binders, it's cleaners, it's dead skin cells. I mean, think about it, it's dead skin cells. I mean, you want dead skin cells in the return duct on the other side of the grill in an OR? It's ridiculous to me. So, before I go on too much of a rant, I'm just going to stop. And I said my piece. Okay, now we're going to talk about strategies, all right? And I'm going to keep this pretty general, so it may not be super specific to your healthcare design, okay? Just general airflow control strategies. You can actually apply this to just about anything. So we're going to look at the measurement requirements first. Where do you want to measure? And we're going to start with basically on the left there, supply relief and DOAS systems. They're pretty straightforward. I mean, you want to measure the ins and the outs. You want to find the best location you can for the total outside air, and then best location you can for the total relief or total exhaust, whatever you want to call it. Okay, and then we're going to, maintain whatever the flow rates are needed for outdoor air and whatever differential we need for pressurization. Okay, some systems might get a little more complex than that, so we may be doing the actual pressure control and the outside air at a ventilation zone. We'll kind of get into that a little bit. Recirculating air systems. Recirculating air handlers are pretty straightforward too, but not everybody always does what's obvious to me. Okay, so, in the case of a recirculating air handling system, we're going to control our pressurization flow by the difference between the supply and the return air flow rates, and we're going to maintain our outdoor air for dilution with an outdoor airflow station. Okay, we're not going to measure the relief. We're not going to measure the recirculation path. These are the three measurement points that we need. I've seen people do everything. This is all you need, okay? And just to make sure that everybody understands on these recirculating air handling systems, I mean, the fact of the matter is you do want to know the total ins and the outs, but they're not typically something you can easily measure, okay? Well, the ins you can measure, but outside air is somewhat compromised where, you're not going to get 2 or 3% on most outside air intakes. You're going to get closer to 5, maybe 5 to 10, depending if it's a rooftop unit. Relief air is often really difficult to measure accurately. Like I said, I don't believe in using piezo rings for any critical measurements like this. I don't even believe in using, our flow meters in the relief fans or something like that on systems like this, okay, where we're talking about we need good differential flow control. What I like to do is say, look, let's look at this, make it really kind of simple. If I look at this point here, I can make an equation. For those of you that are not understanding why I'm saying measure supply return, I can make an equation that says that the recirculated airflow rate plus the outside airflow rate equals the supply airflow rate, and that's an equation I put up there in the middle. I can look at this point here, and I can say, hey, the relief airflow rate plus the recirculated airflow rate is the return airflow rate. So there's another equation. I have two equations. I subtract them. Outside air minus relief airflow rates equals supply air minus return airflow rate. So there's no reason to try to measure outside air and relief, which are normally not as accurate of a measurement as supply air and return air. So that's why I like to go there. There's also what happens when you go into supply and return air. I'm not really showing it on this slide, But assuming you're using good dampers, you could go 100% recirc, and it's a verification method for the supply and return airflow stations, or even a method of tweaking one of those units if they're not located in a perfect location or as good a location as you would like. So anyhow, that's pretty much where I want to go here. Here is equal. Okay, so that's how we kind of get to where we're going to talk about here. Okay, so again, this could be anything. This could be, it could be any kind of a pressure zone, all right? We have a recirculating air handler. It's basically serving just one pressure zone. Okay, it's going to be different if we're serving more than one pressure zone. But if it's serving one pressure zone, we're going to basically, locate the flow meters, supply, return, and at least minimum outside air. And if it's a rooftop unit and you really need good flow measurement accuracy, custom air handler, provide a min-max damper if the flow rates go below 150 feet per minute. There's a reason for that. It has to do with the wind blowing and having the flow meter located close to the outside of the unit. If it's if you're not doing something real custom and it's a package unit, try to select package units where the dampers and where you locate the flow meter are sized smaller than the intake louver or hood, so that these velocities are up. It's not a limitation of the flow measuring device. Okay, we'll measure down to still air. You don't want to control 20, 30 feet per minute, and even if you could, when the wind blows, it would affect it. So that's why we have that kind of guideline there, okay? Now, what we have seen people do, and this is a do not do, okay? They're like, oh yes, we're going to, we're all in on this flow control stuff. We're going to measure supply, return, outdoor airflow rates. We're going to modulate our intake and recirc air dampers or something like that. Maybe it's one or both, or however you decided you're going to do it. There's better way. I'm going to show you some good ways, but at any rate, I'm going to do that to maintain my outside air. I'm going to do supply minus return. I'm going to do fan tracking with my supply and return flow meters. I don't have any relief at the air handler. I may have exhaust in the space. Okay, basically, you don't want to do this. You don't want to control that return fan on delta CFM in the outside air to the outside airflow station, because ultimately when you have this is only when there's no relief at the air handler. These are conflicting, meaning that they're never going to equal each other. The supply minus return differential, because of instrumentation uncertainty, is never going to match the outside air. And so you're going to end up with a hunting problem. Okay, so you don't want to do that. What you want to do is what we're going to show you here. This is the method we do. This is method we do. It doesn't mean you have to do this. Okay? The method that we like, so we say consider doing this, is when there's a return fan and there's no relief, we make the return fan our friend. We use it as part of our strategy to maintain outside air. And so, in fact, we're typically not even using the supply and return flow station. Okay, you would be using the supply airflow station to if you were maintaining air changes, for instance, but not for the pressurization side of this. Okay, because like we said earlier, the outside airflow meter is inherently more accurate than the differential of the supply and return, even with good supply and return flow measurement. So we prefer to do this. Okay, and so anyhow, what we're going to end up doing here, it's this sequence. This is one of these things that I think it's a lot easier for me to do in person. When I have you sitting in front of me and I can point at the screen. And it's not that I can't point at the screen here, but it just, I can't say you understand. Okay, you understand what I'm saying? And it kind of makes it kind of tough, but I'm going to do this anyhow. When you don't have any relief at the air handler and we're trying to, control this outside air, I want to just take you from left to right, and I have three things that I can deal with, that I'm dealing with here. The green is the outdoor air damper, the blue is the return air fan, and the reddish color is the recirculation air damper or the return air damper, whatever you want to call it, okay? It's the same basic thing, but it's in the recirculation path, right? So the more outside air we need in this strategy, we're going to go from left to right. That's how this basically goes. And so we have a startup sequence. And one of the things that are problems with return fans, I like return fans. I like return fan systems a lot, actually. But one problem that you do have with them is the potential for them, if they're not set up right, to blow air out the intake, okay, when you start your sequence. And so what we like to do is we like to start with the return air fan at its lowest speed, okay, which is at the right side of that blue kind of, that blue space on the screen. So there's a vertical line there that we put at minimum speed, and that's going to make the mixed airplane as negative as we can. The supply side can be driven, depending on the system, it could be driven by air changes, it could be driven because it's a VAV system. Whatever is driving it, it doesn't matter. It's going to do that. But we want to start with the return fan at its minimum speed, okay? And the way our sequence is going to work is we're going to, I'm coming on a night setback here. So as we're coming from the outside air damper being fully closed on the total left side of the screen, it's going to go to this minimum position that we've determined. And basically it takes time for the damper to get there. So we limit the sequence to only operate in this area that I'm showing you, okay? And that means the only thing that's actually modulating is the return air fan. And until we get our minimum position. And one of three things is going to happen here. You're either going to hit set point, or you're going to be all the way here on the left, where we're saying, hey, I have too much outside air. And if you set this up right, this typically won't happen. But if you have too much outside air, the only way you can reduce the outside air is to modulate, close the outside air damper. On the other hand, if you didn't have enough outside air, which is possible, okay, so you couldn't, you have your return fan at its lowest speed, you're still not bringing in enough outside air, then you're going to first modulate open the outside air damper, and then if you still didn't have enough outside air, you're going to modulate close the recirc air damper. If this is designed properly, you most likely will never be in that recirculation air damper part. Could happen min-max, undersized min-max. And so we kind of put a little bit of a warning here. It's like you really don't want to be there, because if you actually took this all the way to through the full sequence, you'd actually have all these dampers closed and you'd blow up your air handler. So you don't want to do that. But I always like to just draw the full sequence. Okay, so so in this case, that would be how you control when you don't have relief at the air handler and you have a return fan. It's the most complicated strategy that I'm going to show you. Okay, there is an alternate. There's sometimes we get into cases, not so much in healthcare, but more in offices, large older cities, oversized intake dampers that just don't. You can't really measure at well, because they're so large. That means you can't control them either. The measurement's going to be difficult. So there's all kinds of criteria here that we're going to want to look at. But instead of everything's the same using the return air fan and what we discussed, during startup, being in this one range, and then if you had too much outside air, closing the outside air damper, which could be a real challenge if it's an oversized or poor condition damper. But the next part of the sequence, instead of opening the outside air damper, you actually use the recirculation air damper to bring more outside air in. So you're keeping that outside air damper fixed longer, and then hopefully you're really not in this range where you have to start to control that damper. This strategy kind of, the way this is set up is it makes the outside air damper less critical to your control. Okay, they both work fine. Okay, you can make arguments for both. All right, And again, somewhere in this yellow range, you do have to be careful, you know, how far do you let the recirc air damper close before you open the outside air damper. Setup, we just really, it's a, you know, because you say, well, you got this fixed outdoor air damper position, how did you find that? The way we find it is, you know, we set the system up basically 100% supply air. If it's VAV, all the box is wide open. You know, we set the return fan to somewhere around 80% of its speed. I mean, it's anywhere in that kind of red area that I'm showing there. Okay, to give you some play on both sides. And we used the airflow meter, we used the EBTRON airflow meter to dial up what that minimum position is. Okay, so you want to make sure that everybody's happy with the outside airflow measurement before you do this, or else, you know, you're kind of wasting your time. So get everybody in there, say, yes, I'm happy with the flow meter, but then use the flow meter to set the system up. Okay, like I said, that's the trickiest, and you may not even have applications like that. All right, now supply fan with the return fan. You know, when you have active relief during minimum outside air, and you know, I know we're talking healthcare. This is healthcare potentially because of air changes. It's also schools. It's a lot of different things. Okay, active relief at the air handler. We're not economizing, you know, but we're relieving air. It's a lot more straightforward. We're using the outside airflow station. We're using the outside air damper and the recirc air damper to maintain set point, because that set point is higher than the differential. Okay, and you're using the supply and the return airflow differential to control the return air fan, and you can just go to position really on the outside air. I mean on the relief air. Mistake there. You can go to position and it works fine, but there's some cases where if you're going to come out of minimum mode, like it's more on a DCV application or a variable exhaust application, where you can come out of minimum outside air mode with no relief to minimum outside air mode with relief. We actually will put our bleed sensor, which is a flow meter that just measures airflow and direction, or you can do this with just a pressure sensor. You're basically making an electronic barometric damper, okay? And I guess you can actually do this with a barometric damper too, so that, you know, as you see positive pressure across that damper, you open it. And the reason for that is that when you're not relieving air, using that return air fan strategy that we had just previously talked about, your mixed air is negative, obviously, to the outside of the building, but your discharge could be too, okay, of the return fan. And so you don't want to go from this mode where you crack that outside air damper and that relief air damper, and then you're bringing in outside air through the relief, because you don't know where that relief path is located, or it may not be located where you want it to be. So, you know, at any rate, we prefer that you sequence your dampers for the outside air control and not do an overlapping strategy, or don't just use the outside air damper. There's a number of reasons for that, but I'm going to tell you what we like to do. What we like to do is simply sequence them. So we start by first opening the outdoor air damper to maintain set point, with the recirc air damper fully open, and then if we still need more outside air, we will close the recirc air damper. Okay, so that's the strategy there. The alternate is pretty much what we already talked about. You're doing it with the recirc air damper instead of the outside air damper. So, any rate, it's pretty straightforward on what we would do there. Okay. Again, this is another one of these things where, you know, when you're looking at this in a presentation, you know, it may be one of those things that you say, can we kind of go over that again? Or can I understand what you're saying? Because I can't ask you a question right now. And that's okay. Okay. Just, you know, get back with us on it. okay? The return fan, you know, how the return fans actually work is pretty straightforward. I mean, in this case, if we need to increase the differential, we decrease the return fan speed, okay? When we're economizing, it's not that much different, except that instead of the outside air being controlled to what the outside air set point is for dilution, you know, you're basically controlling to your supply air temperature, and then you're really using the outside airflow station as a low limit device to switch you out of economizer mode or engage some, you know, it really is to switch you back out of economizer mode back into minimum outside air mode. Okay, and so I like to take people from right to left on this, you know, where all the way on the right side of this, we're not economizing, we're in minimum outside air mode. And now we decided, for whatever our reasoning, whether it's, you know, dry bulb or enthalpy switchover, depending on where you are, that, you know, we're going to go into this integrated economizer mode or economizing with cooling, you know. So we're bringing in 100% outside air, we're cooling that air. We finally get to the point where, you know, hey, you know, the outside air conditions are better than the supply air conditions that we want. So now as it's getting colder out, we go into an economizer, a modulating economizer, and, you know, we start to back that down. And this is just a typical economizer strategy, okay? And so we're going to first open that recirc air damper, and then if that's fully open, we're going to modulate down. And somewhere down here, I'm sorry, I didn't want to do that yet. Somewhere down here at the bottom, you most likely would have used that. It would probably be relatively cold outside in most applications, but you would say, oh, you know, I'm going to go below minimum outdoor air. I got to go switch back to minimum outside air mode. Okay, so I mean, you really wouldn't go all the way fully shut. And, you know, it's just, I caution people in this area just to look at it and make sure you understand that about your measurements and your velocities and things like that. Okay, now when you do min-max, this is opinion. Okay, when you do min-max, you have a decision to make. It's like, do I want to when I'm in economizer, do I want to control the max and min dampers together? Do I want to control the min damper first or the max damper first as I'm reducing my outdoor air? And to me, it's pretty straightforward. When you do min-max, one of the problems with min-max is that the maximum airflow path, when you're measuring it, you could modulate down to a flow that's too low to get reliable measurements. And so you don't really want to do that, okay? In my opinion, you don't want to measure in that path. Also, I've seen, and it doesn't matter whose flow meter it is, I've seen when you have these two paths together, there's so much turbulence in that intake plenum that the max flow meter will read something when the damper's closed. So to me, it's not a reliable place to measure. Now, I have plenty of EBTRON customers that are sitting there right now saying, but I do this all the time. It's like, that's fine. You've obviously got a way that it's working for you. But if I'm going to have a general conversation with people, it's going to be, well, I wouldn't do it that way. So what I would do is, again, coming out of economizer is no different, or coming out of minimum mode is no different. We're economizing and cooling. We're using the cooling coil to condition the air. And this next step of modulating economizer is no different either. We're going to modulate open the recirculation air damper. But now we have a decision to make. And in my opinion, and all of this time that you're doing this the way I'm saying, where I've only got a flow meter in the minimum outdoor air, that's the only place I have it, the flow meter doesn't mean very much. Okay, it's not giving you any information of value, really. Okay, but what happens is as you modulate down now, this max damper, and it finally gets closed, Now your outside airflow measurement device is doing what it's supposed to do. If you've set this upright, it is exceeding the max, okay? All right? Your design max, and then you would, start to modulate this down. And again, you'd get to a point where you would potentially have to get out of economizer, okay? Just got to watch the flow rates again. All right, something we can talk about, something I'm sure a lot of you do differently, but the whole point of today is to say, hey, these are things that maybe you've had some trouble with, and maybe this is a better way to do it for you. Think about it, and let's see how that works out, okay? For every case that I say this is the way to do it, you can probably come up with another case where you can say, no, that's not the way to do it, okay? All right, of course, all of this goes away if you simply size your outside air so that you don't need a min-max damper. I mean, the easiest and best way to do this is not need to go min-max, all right? And there are air handling units that can do that, and there's also, obviously, when you add ducted, you can do that, okay? All right. Supply, the fan control is no different. This is how you're basically controlling your differential or your pressurization. All right, so now we're going to look at supply fan, relief fan, recirculating systems, and I don't really treat them any different, except that if we weren't relieving air, we can't use the return air fan as our friend, but that's no big deal, okay? So when we're not relieving air, it's going to be pretty straightforward. We're going to just use the outside airflow station again. And I'm not saying you can't use the supply and the return flow station instead of the outside air station. You can. Okay, even before what I was saying is you can. Okay, but it's typically the differential isn't as accurate as the outside air. So that's why I always go to the outside airflow. But either you could swap these any day of the week if you want. Okay, and so this is how we do it here. I'm not going to do all of the different sequences because I think we've essentially done that. Okay, when we're active relieving air, it's really the same thing. It's identical to what we were doing with the supply return air fan. The difference is we're just controlling the relief air fan. And I've had people say, well, how does that work? How come, what keeps me from bringing in outside air and just relieving it? Well, what keeps you from doing that is you're controlling the supply and the return air flow rates. So as long as those measurements are working properly, you're not going to be doing that. It's not going to happen, okay? And again, economizer, it's really no different. So for us, we run kind of like the same strategy: supply return, supply relief fan. The only exception being supply return fan when there's no relief. Okay. When we get into cases where we don't have any relief that we're exhausted the air handler, I always call, if it's at the air handler, I always call it relief. Okay. But if we don't have any relief or exhausted the air handler, all right, then we have outside air and we have relief air. And when you look at that, that's fine, but keep in mind now that the accuracy can be somewhat compromised on some of these measurements. Outside air may not be accurate enough on some of your units to do good differential flow control. The relief air path may not be good enough. So what that means is that you've got to pay more attention to where you're locating the flow measurement, okay? Is it ducted? There are cases where we'll get into, not so much in healthcare, but we'll get into cases like this where the relief fans are just fans in the ceiling. It's like, I don't think you're going to get a good enough measurement to do this. But, anyhow, the bottom line is you're controlling these two differentials, okay? Fan coils or multiple air handling units, the big thing I want to say here is, you got to get measurement on the outdoor air, whether this is, I'm trying to take one slide to do two things. I'm looking at air handlers on multiple floors or multiple air handlers. And then I'm also saying, well, it could have been fan coils and, could be It could be VRF and fan coils. Bottom line is I want to see you get good measurement on that outside air. Those ducts are relatively small, even on the air handlers. We make equipment that's, ideal for that application, that's cost effective for that application. And, if there's exhaust, you want to measure them. If they're toilet exhaust, that's another story. Toilet exhaust you may not want to measure. You want to just go on fan status. But, the bottom line here is it's just getting if you don't do the differential, let's say this was multi-floor. If you don't do the differential multi-floor, then you have to deal with stack pressure issues, okay? If these are fan coils and, the outside air to these fan coils is changing, maybe based on DCV or something like that, then it's changing the flow into all the other fan coils. So yes, you should measure and control to keep your set point for each one of the fan coils. Okay, multi-floor central station systems. Boy, a lot of times I can't get people to think this way. We have a air handling system serving, 20 floors or something, and we're doing flow control where the air handlers are, and we're ignoring, 10 or 20 floors of stack pressure. I'm not a fan of ignoring that. I mean, the return air duct's a big hole in the building, and if you don't have a way to measure the ins and the outs on each floor, I think you're going to have stack pressure issues. Somehow you're going to have to compensate for that, and so we like to see you measure the total supply on the floor, the total return off the floor. Please don't sum up VAV boxes. Those flow measurement devices aren't accurate enough to use for tracking. Put a separate supply flow station in. We haven't gotten the products yet on the return side. If you're designing this thing from scratch, consider having some way to have some stub duct measurement of the returns. Maybe use our Air IQ package that's a damper, and a flow meter to do that measurement. But if you just leave big chases going up the building on the return side, you're kind of destined to have pressurization problems. I mean, it's just a lot of change in pressure with elevation. I mean, it just really is. Again, we got supply. It doesn't matter to me if it was a supply return system or a supply relief system. We're going to do it the same way. DOAS, putting DOAS in because I think it's very important to look at DOAS, particularly with energy recovery. I've seen too many systems with energy recovery that bring in plenty of outdoor air but ignore the differential, get into a humid climate, and the next thing you know, the walls are soaking wet. Okay, you got big mold problems. Right, you got to pay attention to both. So, if it's a simple DOAS unit and, you're just looking at treating everything like a single ventilation zone, I think you can do this if it's design outdoor air, not DCV on multi-zone. But if it's multi-zone, you got to really think about it differently, which I'll get to. You want to maintain that flow differential, and you do want to maintain your set point as well, okay? When we get into DOAS designs, and this is more like schools, offices, theaters, things like that, but it's worth talking about because it still could be part of your design, particularly when you're doing DOAS. Okay, not DOAS, completely, when you're doing DCV, demand control ventilation. And demand control ventilation could be that you have a CO2 sensor in the space or you're doing some kind of occupancy counting, but it could be simple occupied, unoccupied type of DCV, like you just cut some ventilation zones off. It's like when you look at the outside air side of a DOAS system, that's multi-ventilation zone, and there's going to be some variable zones on, DCV. it's like saying, it's almost like a VAV system from the supply side. I mean, you would never think about controlling your, your temperature zones on a VAV system without maintaining flow rates, okay, without measuring it. And so I strongly suggest you measure the flow. And I think that this is a case where when we do DOAS, the one nice thing about DOAS is we talked before about dirt and dust and stuff like that. And in that, it could affect some measurements. It doesn't on the supply side of a DOAS system. I mean, these things will last 20 years. Okay, they'll outlast your system. So, put in good measurement. It's not that much more. We make specific equipment for these smaller ducts. Put in good measurement and set it up and walk away and be done with it instead of having to come back because your VAV box flow measurement drifted every year because the pressure sensors drifted every year. Okay, this is a fantastic application for our equipment. Okay. And I keep saying drier climates, but I mean, if you don't do anything, I'd like to see you at least do this. Now, if you go here, notice I have flow measurement. I have some redundancy of flow measurement. This was the slide I was just on. I'm doing some redundancy of flow measurement on the supply side. The reality is, if you're using EBTRONs on the supply side, you can just sum them up. Okay, you don't have to do this. Okay, so it just depends on the equipment. Sometimes you're buying equipment and you want all the measurement to be in the piece of equipment, so that's this one. But if you're not, that's this one. Okay, same deal. When we get into really humid climates, and it's a lot of them. I say really humid climates. It's really anywhere east of the Rockies, but getting people to buy into this has been relatively difficult. You really should treat ventilation zones on a DOAS system not much different than you even think about how you're doing your operating rooms and stuff, meaning that you want to control the ins and the outs because you don't want those individual ventilation zones to go negative in a humid climate. It's a problem. So this is what I'd like to see people do, but they don't do enough of it. Okay. Okay, now we are going to talk about technology, and that's kind of where we're going to finish this up. Okay, so it's like, okay, you have choices out there. I mean, there's a lot of these applications you do have to do measurement. So it's like, what should I use? Okay, and so it's like, why choose thermal dispersion? And specifically EBTRON thermal dispersion. All right. Well, one reason to use EBTRON thermal dispersion is we've been doing it for 40 years, but really the technology itself is ideal for HVAC because as the airflow it goes down, as the airflow rate goes down, the sensitivity increases, and that's really good because most, if not all of our HVAC applications are relatively low velocities. There's a few that are really high. Fan inlet measurement is right on the border. What I would say is we're starting to get high, but we definitely can measure there. But when you get down to things like supply and return airflow rates in ducts or outside air intakes, those flow rates are pretty low. So having a device where it has its most sensitive at the low flows is really great. When you compare that to pitot tube arrays or air wings, which are really pitot tube arrays, piezo rings, and other delta P devices, you have pretty much a square root relationship where the sensitivity decreases with flow. So that makes those devices not really good choices typically when you have lower flows or a lot of turn down. Okay, so when you look at these devices, what am I talking about? What is DP devices? Well, pitot tubes, pitot arrays, air wings, they're basically devices that will average the velocity pressure, okay, and then that velocity pressure goes to a single pressure transducer that will then convert that velocity pressure to flow. And you have to understand that the accuracy is a combination of the uncertainty of the array and the additional measurement uncertainty of converting that differential pressure signal to the airflow rate, okay? The same thing's true with piezo rings. The only real difference with piezo rings for fan inlet piezo rings is that the pressures are higher. But when you look at the pressure sensors that are used, really the accuracy classes are all about the same as you're using on DP. The turn down's the same, and actually the effect is about the same. And when you're doing a piezo ring, you're using the inlet cone as the fixed orifice flow meter, and so that every inlet cone is a little different. They're not precision machine devices, and so that, you know, the flow coefficients from one to another vary. So there's measurement uncertainty there. Other differential pressure devices that have similar problems or, you know, or similar issues is like measuring a DP across a louver. You know, a louver is relatively low pressure. You don't know the flow coefficient. You got to set it up, but the relationship to flow is the same. And then there's even other devices out there that measure, I call it measure the pressure drop across obstructions. And again, very similar situation, but all of these just use a single pressure sensor, okay? And so one of the things we have to look at is pressure sensors. So you have a relationship. This is a square root relationship. I know some of you say, oh, that's a square relationship. Well, the way I have the axes, I have pressure one axis and velocity on the other, but it's really a square root relationship to flow, okay? And so you have this relationship like we're seeing here to velocity and pressure, and it doesn't matter. Like here I'm going to say, you know, we're going to look at the sensitivity decreasing, but here I'm going to say the full scale of the pressure sensor, and in this case I'm showing, you know, 0.25 inches, which is something you'd apply to a pitot tube. But it could have been 25 inches, something that you apply to a piezo ring. It doesn't really matter, okay? I've often thought about just taking the numbers off of the screen, but I'm going to leave it this way, you know, for now. And basically what happens is if you look at the uncertainty of measurement, okay, that full scale will give you some full scale velocity. Now there's some uncertainty of measurement on it, okay, and that projects some uncertainty in flow. All right, and normally speaking, at the top end, there's not really a significant problem here, okay? But most of the pressure transducers we use today their accuracy is as a % of full scale. And you're also not using it at the full scale velocity of the application. So you're probably somewhat less, and you have some turn down. So here, you know, the sensor could read to 2,000 feet per minute, but the application was 1,500. And let's think of feet per minute for this today, and we're going to do 3-to-1 turn down to 500. All right, so now we look at 500, and it has a certain DP associated with it. Well, because you're using a % of full scale pressure transducer, okay, the uncertainty is theoretically the same at turn down. So when you look at, you know, what that uncertainty in flow measurement is, it's huge, and it's not intuitively obvious to people. You know, the accuracy of these DP devices varies with the square of the turn down. You turn it down 4-to-1, you're 16 times less accurate. Okay, and I don't think that's obvious to people. And you know, it really matters on the selection of the pressure sensor. And you know, some of these pressure sensors are marginal in performance for using them for flow measurement. They may be fine for using them for pressure measurement. And so what you want to do, and this is just me putting it together for you, is just looking at different % of full scale accuracies, and I'm putting 0.1% to 5%, and looking at the airflow error as a % of reading based on the turn down of the full scale of the device. So 100 is the full scale of the device, and you might be running at, you know, 50% of the full scale of the device. Well, all of a sudden you see, well, the uncertainty from the pressure sensor alone is large. And you might say, well, my pressure sensor says it's, you know, 0.8% or 0.1, you know, 0.5%. It's like, yeah, that's out of the box at room temperature. Did you look at the temperature coefficient spec? Did you look at the annual drift expectations of it. And a lot of times 0.5% pressure transducer will end up closer to 2%. So you want to pay attention to that, okay? Because with turn down, there's some significant error there, okay? The other problem with DP is you're only using one sensor. So you have you have a non-linear response to flow for each one of these points, and you're basically averaging them, and it's just simple basic math. If I'll put pitot tubes up here. If I have 3 pitot tubes, like an air balancer uses, and I measure 3 points, I have to take the square root of the velocity pressure at each one of those points before I calculate the flow, and that's essentially what that equation on the top left there is. But what an averaging device will do, the best it can do, is give you the average velocity pressure. Doesn't matter what it is. Like I said, it could be a pitot array, it could be an air wing, it could be a fan inlet, piezo ring. It's even worse on a series of piezo rings on a fan array. I'm just going to show it on this one way. I don't want to spend all day on this, okay? But anyhow, apply some numbers to it. These aren't equal. Apply some numbers to it. Here we could be. This is a downstream of an unveined elbow. So we have very high velocity on one side of the duct, 2,200 feet per minute there on the left side, on the left sensor, and 500 on the right sensor. And if everything was perfect, okay, you would have calculated the average of this example to be 1,500 feet per minute if there was no error in any of the measurement, okay? Yet the best that the averaging arrays can do is give you that average of those 3 velocity pressures, so the 0.3 to 0.2 to 0.015, which is 0.173, and that's the best it can do. And if you calculate the velocity based on that 0.173, you get 1666. It's 11% off. And that's that's just math. That's no error of the measurement, no measurement of the measurement device, no cross flow through the device, none of that. So it's a significant problem. And if you come to Brain Guest, I've been doing this with our group now for over 20 years, the same example, and it's not to show anybody being bad. It's more to show, hey, there's a difference between a multi-sensing point device that independently processes each one of its sensors and another device that averages a nonlinear flow signal. Okay, so we'll take off our flow meter and we'll put it in a reference position, which is a really good straight run of duct, and we'll move it to really bad locations that we wouldn't recommend and what we show wouldn't recommend, okay? And, but anyhow, when we show, like, for instance, how the EBTRON works, and this is typical, it varies a little bit from time to time, but not much, okay? You'll see that as we go from these different positions, we do get some variation in the flow, but it's very small. Remember, it doesn't meet our guidelines, okay? And when I do the same thing with an averaging pitot array, it's not even close. So, it's just to say, hey, listen, there's a difference between these different technologies. And I could do this with anybody's pitot array, anybody's averaging pressure device. It's just the way they are. I mean, you got one sensor, okay? So, and then, finally, vortex shedding, it's out there. It's been out there for almost would say as long as we have been around. And one of the bigger problems with vortex shedding is that it just can't measure lower flows. Okay, I mean, basically you're getting they're measuring low audio frequencies. It's a device that's the response is somewhat linear to flow, which isn't bad, but it's airflow, not mass airflow. Okay, and so, the problem is primarily lower flows with these devices. Okay, so when you look at them all, you're like, hey, what's the best choice? Well, it should be thermal. And really, though, is it EBTRON thermal or is it thermal? It's basically the thermal principle in general is the best technology, but now, why EBTRON? Okay, and so when you look at the why EBTRON, well, let's start with EBTRON started in 1983. I started in 1984. For those of you that are out there, this is not what I expected to make a career out of by any stretch of the imagination. This was just something that I was been doing over a spring break job I had. And but anyhow, I got there in 1984, so I've been there, going on 41 years. And Mike Urbaniak and I, who still work together, he started there in 1984 on the design side of this stuff. And so we've been around for a long time, and we kind of crack up some of the new employees. My VP of operations, for instance, he's only been there 30 years, so we call him the newbie. So we have people that have been there for a long, long time. Okay, and you'll realize that if you've worked with them for a long time. We pioneered the direct outdoor airflow measurement for monitoring control in 1989. We saw that coming because of the changes that were coming in ASHRAE Standard 62 in 1989, positioned us well to develop a device to measure those flows, wide temperature ranges, and come up with the control strategies that we needed to make them work, okay? And our technological advantage the whole time has been this thermal dispersion airflow measurement using bead glass thermistors, okay? So what we've done since 1983. We have a very good manufacturing facility. I'm going to show you a couple slides quickly from it. And to me, we're a measurable difference. I mean, I still do this 40 plus years later because I feel pretty good about it, okay? And I think everybody that works with us feels pretty good about it, and our customers that use us feel pretty good about it. Things that we do have made quite a significant investment in manufacturing. And so we do have a surface mount line that we use that does all our circuit board assembly, which is very important. It was critical during COVID because we could make on-the-fly changes as components became not available and do smaller board runs. We have something called a selective solder machine. Really, there's not a whole lot of people interaction in the actual assembly of the transmitters and the circuit boards. And that's great, okay, because that means repeatable, you can really control your, your quality, okay. Same thing's true in pro manufacturing. We're in the process of actually expanding our facilities, moving across the road, bringing in automated equipment, one of them for pro manufacturing. Again, it improves product quality, it improves throughput. It's just good practice for us. That's the direction we've been going and the direction we continue to go in. For the most part, all of our test and equipment is designed and built in-house, maybe with the exception of that high-performance meter you see on the desktop there, but if you even can find it, but we go through extensive burn-in periods for the electronics. We bring them into our automated test fixtures that calibrate them and test them. There's quite a few QC points. Many QC points along the line, flow calibration, everything. It's a pretty state-of-the-art system, okay? Now, for those of you that aren't completely familiar with EBTRON and how it works, basically this is the way it's worked since 1984 when the company first started producing products. Where did we start with this slide? I could have done this with animations, but basically when you look at the left side of the screen there, that gold vertical little tube, that's our probe design, okay? And what you're looking at is an individual sensor node. So there could be up to 16 of these sensor nodes in your duct, okay? But each one of these sensor nodes has two thermistors. And one thermistor is self-heated, which means we pass a little bit of current through it, we heat it up, and as a result we can measure the power dissipated to the airstream, and because it's a thermistor we can basically determine what its body temperature is. We have another one we call a zero power thermistor, which is microamps of current,
no self-heat, it measures the ambient air temperature. And so when you look at that little relationship near the middle of the screen, from your perspective, I think this is all you really need to know. If you know the power and the delta T, you have a relationship that's proportional to the velocity or the mass velocity. So that's how a thermal device works. That's how ours works. There's people that do it differently than we do it, but this is how we've done it for the last 40 years. Okay, and so we were real early on. We looked at this in the beginning, and they were the original EBTRON in 1984 was an analog circuit. Okay, and then in 1985 and 86, we released our microprocessor-based device. We're the only ones that use a bead glass thermistor, which is really a high-performance thermistor for temperature measurement. It's been designed to handle extreme temperature changes, much more than we're going to see in HVAC. They're hermetically sealed for long life. They're actually oven aged for extended periods of time. It gives them stability. They are variable parts, so we have to take each one of them and we have to put them in multiple controlled temperature circulating baths to get the resistance temperature characteristics. It's one thing that I think has kept people out of using this device. It's just not something you just walk off the street and say, I'm going to start doing bead glass thermistor thermal dispersion flow meters, okay? And then the sensor itself is potted in a marine grade epoxy, so it's waterproof. It's not affected by salt water or atmospheric acids. Okay, well, it's just a good design on the sensor node. Okay, our competitors. I only put this in here just to say that they're not the same. I mean, I'm tired of hearing people say they're the same. Ruskin and Air Monitor currently use chip thermistors. Okay. Chip thermistors aren't the same as these bead glass parts. They mount these different. Ruskin does very similar to what we do in terms of, a self-heated and non-heated. Air Monitor actually uses a heater and kind of keeps the temperature differential constant, measures the power to the heater. They're just not the same animal, okay? What I tell you all the time is, so if you want to find out if you like these stuff, go buy it and use it. Okay, and see if it does a job for you. Okay, I mean, we're here to talk about EBTRON and why EBTRON is what it is, but we're not all the same animal. Okay, I talked about the sensor node ruggedness. I mean, we have the salt water and acid bath study that we sent out for independent testing. It's not just a salt spray test; those are actually sensors that have been put into a heavy salt bath that then we've evaporated out the water. They have to all pass and function as they did when they were put in. We put these parts over fuming acid baths because we know that things like outdoor air get salt, a lot of salt in the air. We get sulfuric acid in the atmosphere. We've got, there's things that are in the outside air that aren't great. So, that's what we do. Accuracy and stability. We take our Cal standard directly to NIST. We actually accompany it. They give us a report on calibration. We take that standard. We transfer the calibration to our production tunnels. The stability part, kind of hard to see there on the right, but that's a 10-year study of resistance temperature characteristics of our part. So what we see is that red line is the statistical best fit line through that data set. We have no statistically significant change in electrical resistance of this part over 10 years. I could tell you that is not the norm for thermistors, but it is the norm for ours. Okay, so a very stable part. Like I said, we transfer the calibration to these tunnels. Each individual sensor node is calibrated in these tunnels. So each individual one, okay? So we calibrate them in these tunnels. I'm showing our probe design right now. So in terms of the number of points and things like that, we'll calibrate our typical probe thermistor sensor nodes at 15 airflow rates plus 0, so 16 points, between 0 and 5,000 feet per minute, each individual one, okay? And as a result, they become a percent of reading device, Okay, we don't care what you're going to use them for. We don't ask you some full scales. Every unit comes out of the factory the same, and in fact, if you can see that little slide on the left, typical reported calibration on an individual sensor node shows that the percent of reading accuracy is typically under 0.5% of reading. You looked at the average, it hovers around 0. We don't tell you that that's the accuracy of the device. We say our sensors are accurate to 2% of reading. And then we go to installed accuracy, which is what we say is what you should expect for your application. So that's based on the number of sensor nodes and where you locate it. And it could be 3%, it could be 5%, and there's some lower sensor density applications that might even be higher. But we're trying to give you realistic expectations of performance, not some bull that we get out of a lab for sales and marketing purposes. You either appreciate that about us or you don't, okay? Each individual, this is a probe again, basically the sensors are very variable. They all have to be calibrated. And if you ever look at one of these tubes, you'll see that there's barcodes on each sensor node. It's because in the manufacturing process, we have to retrieve all that calibration data and we have to store it in a serial memory chip at the connector of each one of these probes so that when you plug it into the transmitter, all of that calibration data is transferred to the transmitter. It doesn't matter what model unit that we're doing. Okay, and then all we're doing is, converting all these signals to binary. So we're doing high performance A to D converter, converting, all these voltages to binary, push and shove in numbers, calculate the temperature, calculate the airflow, average it, output it. Very sound. I want you to think about this. If you buy an EBTRON that has 4 probes, 4 sensing nodes per probe, okay, so 16 sensing nodes, you've essentially purchased a device that is 16 independent airflow meters and 16 independent temperature meters. I think that's a pretty good deal, okay? They're all independent, all right? Think about that. Additional functionality, things that you don't use, that you should be using, okay? All of our devices come with velocity weighted temperature, except for one model of our X1000-T, because it only has one analog output, the A1000-T, and it just has airflow. But every other device has airflow and temperature standard. But it's not just temperature, it's velocity weighted temperature. What's the difference? Okay, well, a lot of times when you're doing these measurements, you're measuring at a point or a couple points, but you're not recognizing the fact that when you have a velocity profile, you have to weight the temperature. So just look at this very simple example. The top of the duct is 5,000 CFM, the bottom of the duct is 2,500 CFM. The top of the duct is 80 degrees, the bottom of the duct is 70 degrees. What's the temperature of that airstream? It's not 75. It's twice as much air at 80. It's 76.7. And I tell people all the time that use this stuff, there's a lot of applications for where you need good measurement, temperature measurement. Use this device. It's a great device on your outside air for making a decision for those of you that do dry bulb switchover. And then on the other side of it, we added a humidity sensor, and it's the same deal here. I mean, we've got, I'll use the same temperature profile, but now when you look at this, and again, it's another tough little thing to see on a webinar. But basically the top of that duct is 41% RH, and the bottom of the duct is 58% RH. I mean, I'm rounding, but the big deal is the BTUs per pound. If you were using this for wet bulb switchover, the top of the duct's 29.1 BTUs per pound. You're not economizing. The bottom of the duct is 26.6 BTUs per pound. You are. So where did you locate your enthalpy sensor? And the bottom line is, even if you use the average temperature, it's not right. You have to use velocity weighted temperature. Okay, so velocity weighted temperature, you find that the actual enthalpy of that airstream is 28.3 BTUs per pound. And that's it for for economizer switchover, I see people that are measuring in the wrong place. What you want to know is what is the enthalpy of the air entering the mixed air plenum, not on the roof. What is the air mixing with the return air? And it's what's coming through your outside air intake. And so this is something I think people should look into more, use more when they're doing, when they're putting our flow meters in outside air. Of course, there's plenty of other applications where you want to know these different things. I mean, we basically we provide you with a velocity weighted temperature standard, velocity weighted humidity. Once we add this humidity sensor, you can get velocity weighted humidity, velocity weighted enthalpy, or dew point. Now that's only on our Gold Series product right now, but that's most of what our business is anyhow. Okay. When it comes to connectivity, we've got you covered. Okay. We've got linear analog output signals. We have RS-45 that's field selectable between BACnet and Modbus. We have Ethernet that's also field selectable between BACnet and Modbus. We have a couple variants of their Ethernet cards coming out shortly. I'll explain why in a few minutes. And then we have the, LawnWorks. It's not as much of a demand as it used to be, but it's there. We have a data logger card. We have a lot of different things that we can talk about. Products. Really, our reps are well versed with products. We have our Gold Series. That's what we sell most of. High sensor density, most functionality. It's what I would apply on most of my larger duct systems. What's larger? I don't know, anything over 2 foot by 2 foot, maybe. Low sensor density stuff. Pretty much very similar to the Gold Series on under 2 foot by 2 foot in performance. But as the duct size gets larger, it has less sensors. So because it has less sensors, the installed accuracy uncertainty increases. It doesn't mean it's not going to be as good as a Gold Series, but the probability it is not there because of velocity profiles, okay? But they're same technology, same flow measurement technology. The Gold Series has more functionality. Excuse me. It's hard to talk for a long time. On the special tool side, on the Gold Series, okay, every one of our products comes with this, every one of our Gold Series products comes with the low energy Bluetooth radio unless you request it without it. And if you request it without it, you can't add it in the field. And the reason that you would want to do that is we do a lot of data center work and government work that doesn't allow radios. But for most of the applications, it's only a read device. It's a read-only device. You can't change anything with it. So you'll get basically the first screen. You walk into a room actually, and you get this app going, and the first thing that you see is what flow meters are in the room. We allow you to give us up to a 16-character name when you order it. I suggest you do that because it makes more sense to walk into a room and see something like this that says AHU5 return air rather than the serial number of the unit. You can change it in the field, but to me it makes more sense to just name it in the first place. It'll tell you the model, it'll tell you the area, it'll tell you what the EBTRON integration is, which means we integrate the information in the transmitter so that if you, like this case here, it says integration 100. EBTRON samples every 300 milliseconds, calculates flow every 300 milliseconds on a 1 to 16 sensor unit, okay? So, 100, integration buffer of 100 means it takes 30 seconds for it to do an integration of 100. You don't want to sit there for 30 seconds. So we have an integration buffer in the transmitter that's always keeping the last, in this case, for the integration buffer is 100, the last 100 data points. So that when you shoot this thing at the transmitter and get back the results, it's instantaneous, you're not waiting. Okay, so, what do you get? You get everything that you can see on the display. You get the flow, you get the temperature, if you have the humidity sensor in, you get that, you get, whatever you have it set up to display is what you're going to get. There's some airflow alarms built into the unit. If you use them, it would show you if they were active. Trouble codes, meaning is there anything. The transmitter is pretty smart. It's always looking for problems. If it sees one, it'll give a trouble code back, and you'll know that something was wrong, okay? If somebody went in and adjusted the EBTRON, this bottom will show up. It says flow adjust on. You can turn it off to see what the EBTRON read out of the factory. It does not affect anything in terms of what it's reading at the device, okay? What the output of the device is. It's just you on the phone. Another screen you could go to is this traverse data screen. This was developed for balancers, but it's really a good troubleshooting thing for anybody. You can get the individual airflow rates and temperatures of each sensor node across the network if you were using, RS-45 or Ethernet, but also you can get it with this device. Okay, so it'll show you the individual sensor node flow rates and the individual sensor node temperatures, as well as what else is displayed on the screen. You can save this data, you can email this data to yourself. And finally, there's a diagnostic screen that'll show you what all the parameters are set to, as well as, what any active trouble codes, any historical trouble codes. And what you do there is if you have a problem, first of all, I think it's a good thing for you to go out and just shoot this and save it if you made any changes, to the device. But the other good thing about it is, you have some questions, something isn't working right, you don't want to get on the phone with customer service and go back and forth. You simply click the Send to EBTRON Service button. It'll go to the service department so that when you call the service department, it's all there for them to look at. The other beauty of this thing is we do not charge for this application. We do not charge a maintenance fee for this application. It is not a recurring source of income for us. Okay? We update it, we manage it, and we keep it current, and you don't pay for it. Okay? It's just something in the way that we operate and how we do business. Application-specific measurement, so when you get into smaller RTUs, maybe the EBTRON Gold or Hybrid isn't the right solution, so we have a product for that small. I'd say, ideally 6 ton, 10 tons maybe pushing it, but 5, 6 ton units. You have these rooftop units on schools. You should really measure the outside air on them. You have some desiccant wheel energy recovery units that I think this is perfect for. You can get the airflow of each side of the wheel with a single device. Okay, you just set the transmitter up to output both. You can use these devices on terminal boxes. Sometimes people will use them on VAV boxes to get more turn down on traditional type VAV or labs. We'll also use them for tracking on smaller duct systems. They're perfect for most of your DOAS applications. It's basically a stripped down version of the EBTRON, okay? And so it's something you should look at and make sure you understand that we have, okay? Fan inlet measurement. We have devices that are designed for single and dual inlet fans as well as fan arrays, okay? So that might be something that you want to measure. All right, don't let anybody tell you that these devices affect fan performance because they do not. Okay, this is a plenum fan. This is a Greenhack plenum fan, QXP24 model. And if you look at each one of these screens, what you see is you'll see the fan with no obstruction, top left. You'll see what the drive output is, and the current draw is what I'm particularly interested in. On the top right, so it's 13 amps there. The flow that you're seeing on the bottom left is the flow as measured downstream of the fan in the duct. So we're not measuring it in the fan in this case. Okay, at 10,250 CFM. And then the sound level is us having a sound meter upstream of the fan. It's kind of an arbitrary location we picked, but it's just right upstream of the fan. And that's 90 dBs, okay? We put in our flow meter, which is made for these plenum fans, and you'll see there's really no difference. The drive current draw is no different. The The flow's basically the same and the sound level's no different. Okay, we put a pitot array in just to kind of show you the problem that they have with plenum fans. The problem with plenum fans is if you put something in the throat of the fan, small throat of fans. And so here you see a pitot array. We could have put an EBTRON that goes in the throat there. It would have similar result actually. You know, the current has gone significantly higher, the flow has gone significantly lower, and the sound has gone significantly higher. Okay, but that's not what we're doing. Okay, when you get to fan arrays, the EBLink has an additional screen which will show you the individual flows of each individual fan. We have some specialty measurement devices outside the scope of today. The bleed sensor is a pretty cool device. It measures airflow and direction in a 1/2-inch pipe. It's got lots of different applications, but way too many to talk about today. And we have a counting device that uses thermopiles that measures the number of people that goes through a door. It's bi-directional, and it's not a bad thing to use for DCV, but there's other applications where people just want to know where is, how many people are in the space, okay? Ultimately, we're still the better mousetrap. We have great technology, a 3-year warranty. We have an advanced replacement policy. We have local representation. We have toll-free customer support. We still have real people on the other end of that phone, okay? Where I'm gonna kind of finish this up is with an exciting new product that we have that has just been released. We've used an older name of ours, the IQ Enforcer. If you've been with EBTRON for a while, you remember in the 90s we had something called the IQ Enforcer, and where you brought a lot of flow meters back to a central processing panel, we called it. This is by far a different animal, but we kept the name because why not? So this is a device that we've designed and manufacture. It's kind of built on the idea of a tablet or a phone, but it's not a tablet or a phone, okay? And, it basically is designed to have resident applications that you add or update over time, okay? So it's not a single use type of device, okay? The model that I'm showing here, the SDX 1000, is the first model that we're releasing of it. It's a 7-inch diagonal capacitive touchscreen, so it's what's on your phone. And this model is 900 megahertz micro and with 512 megabytes of RAM and 8 gigabytes flash. It's a pretty powerful device. This version of it is an Ethernet version, but we call it, it is true Ethernet, but we call it, Ethernet, EBTRON Ethernet, because we don't want to go out, particularly initially with this device, on your Ethernet network. We want you to run an independent network between our devices. We just don't want to get into that, but it's not that we can't, it's just that we don't want to, okay? So it's compatible with any EBTRON Ethernet devices, which right now is our GTM devices on the Gold Series, okay? But anything else that we do, EBTRON, or even our sister company, Greentroll, that's Ethernet, or anything else we decide to approve, okay? And I said you're not using this Ethernet to connect to your BAS. No, in the Gold Series and that GTM product, for instance, you're using the analog output signals to connect to it. Now I'm going to talk about various release phases that are coming that give you more connectivity flexibility, okay? But we call it bus Ethernet. But it really is Ethernet, okay? So it comes with a lot of really slick displays, slick applications. Wait a little while. Slick applications here. One of them is configure, okay? So one of the beauties of this device is you locate, let's just think about a mechanical room as an illustration. So you have all these different flow meters in the mechanical room. Supply, return, outside air, maybe you have 2 or 3 air handlers, okay? This device will support up to 16 individual devices or transmitters, okay? So you have this in a mechanical room, And you want to be able to do everything from this one point, okay? And one of the things you have to be able to do is be able to configure it if you want to modify or look at how this unit is set up. The nice part about this, and I'll say this again, I think in a slide or two, but the nice part about this is we see people a lot will take the transmitters and they'll locate them at eye level near the control panel so they can see them. And they add extension cables to the device and to the EBTRON, which is relatively, it's costly. Okay, I mean, these cables are, 24 conductor, 25 conductor cables with gold plated pins. So we're like, just locate the transmitter where you can get to it if you ever had to service it, okay, but not so you have to see it. And then you basically run this Cat5 down to, right now, through an Ethernet switch for multiple units and then back to this display, okay? Well, it ends up that the way this is priced is that if you just save two 30-foot extension cables on two 4-sensor probe locations in the mechanical room, it paid for this. So, because I've had people say, well, how much is this going to cost me? Well, if you're using it the way we intended to, and you've been doing extension cables to bring the thing down to eye level, it's not going to cost you anything. And it's cost-wise, it's built around like cable extension cost. So one of the applications is configure, because you got to be able to configure the device, so you can configure it, okay? Another one is just a summary. It just shows you everything that's connected, and a device may have, like the Gold Series transmitters, for instance, if with the humidity sensor, it has 5 outputs, up to 5 things that it's measuring, right? It's got, airflow, temperature, humidity, enthalpy and dew point. So it's going to show all that for that device, and all the devices connected. I like the summary, the screen quite a bit. And you can't see it here, but it's a scroll up and down type of thing, so you can see everything. Display is probably how you will set it up to run most of the time. You'll make this run in the foreground all the time, and it'll just scroll through all the units connected. You can click on it to stop it on a single unit, or you can jump to a single unit that you want to look at, okay? And like I said, it'll show everything about that device that's connected. And then it has the EBLink reader built into it. And I think we're going to be enhancing that because it's one thing writing for a phone, it's another thing writing for this, okay? So that to me makes it a really great device, okay? It's kind of like a little summary thing here. It's like, hey, what do you get? You get the display, you get a power supply. It comes with free applications. Right now there's 4, but there's others we're working on that you'll just be able to upload. You're like, how do I do that? Do I need an internet connection? It's like, no. The way we did it is there's a USB connection. You do it with like a USB thumb drive. That's how you update this device. You go to, EBTRON.com, and you go to where we have these updates or new applications. You download them, and then you install them, okay? What's not included? Well, there could be fee-based applications someday, but there isn't right now, okay? And we don't provide the Cat5e or higher cable, and we do not typically provide the Ethernet switch. We do have the ability for you to purchase an industrial Ethernet switch from us, but we don't make it, so we can also give you the specs on that if you prefer. Okay, some people want a package, some people just want to go ahead and get it. Commercial switches work fine. Just remember, commercial residential switches are just that, residential switches. The cost advantage, I kind of said already, 30-foot extension cables on 2 4-probe measurement locations equals the cost of the display. And it's got lots of advantages, okay? The phases that you probably can't read is the phase now is our GTM devices, which is basically our Gold Series with analog outputs, isolated analog outputs that you've added an Ethernet option card to. Most people are currently buying that product with the RS-45 card and not even using the RS-45 card. So I think this is a good swap. Go to the Ethernet card as standard, and then that's how you connect to it. And that's this first release. There's a second hardware release where we're making an Ethernet RS-45 card so that you connect to our device with the Ethernet card, and you can connect to your building automation system either with the analog signals or the RS-45 or both, okay, depending on how you want to use it. Then there's a third phase that we're finishing development on, which is an Ethernet card, which is really, what we're really saying is it's an Ethernet switch, but it's an industrial grade Ethernet switch, because that's what we do is industrial grade temperature ranges on our stuff. So that'll allow you to daisy chain the Ethernet, okay? Or use the Ethernet for your own Ethernet network if you want to keep it separate. I don't want to bother going into phase 4 yet, because we got to get to phase 3. But there are different phases of this. We do have an RS-45 version of it. I don't know that we'll ever release it, okay? Because I think this is really the way to go. But anyhow, that's the SDX 1000 on, under the IQ Enforcer system. And I already talked about the standard installed applications, but it's live display, device configuration, device summary, and Evelyn Creeder. I do want to briefly mention what's coming. All of these are kind of laid out in terms of what they are. The deal for us is, is getting honestly enough manpower to finish them all, okay? But I will go through with you what they are. One of the applications that are coming is, and these are all free apps, and you can add them down the road, okay? The Field Match Wizard app, we find that there's a lot of cases where people put these things in the supply and the return, and of an air handler in particular, and they go 100% closed loop, and they want to match one to the other. Maybe one's not in a good location or a marginal location, or you actually want to tighten them up. We actually can show you that if you use this Field Match Wizard and you have low leakage dampers, you can bring these flow meters to, within 0.5% of each other. So there's some advantages of doing that for pressurization. Fan array monitor is another one that I want to see happen soon. So if you look at our display app, it shows you the actual, average output, the CFM output of the devices, but there are people out there that have requested, hey, I want an app that I can click on and look at my fan array and see the flow from each one of my fans. And that's fine. So that's a fan array app. The trend log app may be put on hold because most of the time people are using this, have a building automation system that can do the trend log, but obviously we can do it. Indoor air quality monitor is going to be tied into some green troll products, CO2, VOCs, other sensors. CO2 airflow occupancy counter. If you come to my DCV stuff, you'll realize we have a way to estimate population that way. Multi-zone DCV ventilation calculator, that's probably off the longest. The Tab Delta CFM setup system is pretty interesting too. I'm not going to get into details here, but it has some, other than just say that it uses wireless pressure sensors to help determine what the flow differential needs to be for pressurization. The thing that affects you folks is this operating room, ISO room setup monitoring system. I'll just talk about it a little bit more on the next slide. And then whatever else we can do over time, okay? The healthcare app that I think is going to be very useful for those of you that really want to get to the next level in monitoring and for pressure control is basically we're going to add a pressure sensor to the device, to the system, okay? And the idea here is that you use the pressure sensor to fine-tune the return. You have a supply flow measurement in the say we're doing an OR. We have the supply flow measurement in the OR, and then we have the return flow measurement. You could go and try to measure those with test and balance, and you're going to be 5 to 10%. Or you can say, hey, I located them in the right location, and it's 3%. But you may need cases where, because the rooms are getting tighter and tighter and tighter, you need better accuracy than that. So one way to do it is to is to look at the pressure of the space, dial the return flow in so that the pressure of the space is 0, and then realize that that means that the return flow and the supply flow are equal, and then you match the return flow to the supply flow meter. It's an in-field setup, okay? But I think what it'll do is you'll set it then up at the operating conditions for like an operating room and a setback condition for the operating room. And now you're pretty close to being able to do unoccupied setback that works.